Okay, so now question number 17, subpart B. They're telling us to actually find the equation of the line passing through the point negative 1, 3, negative 2 and perpendicular to the lines, and they've given two lines in 3D space. So since whatever this line is, it's going to be perpendicular to these things. Let's first write like a basic general equation for any line in 3D space. So any line in three-dimensional space is represented by x minus a over p is equal to y minus b over say q is equal to z minus c over r. Okay, and since they're saying that it's perpendicular to this line, so let's use this formula. So we know cosine theta from, I think, the very first question, subpart B. I had given an intuition for the angle formula between two lines is equal to, well, this p times, rather the this direction ratio of this line times the direction x direction ratio of this. So p times 1 is p, the direction plus direction ratio of this y times this direction ratio of this y of the second line. So 2q plus 3r similarly, divided by the magnitude of p squared plus q squared plus r squared under root times square root of 1 squared plus 2 squared plus 3 squared. But since we know that these lines are perpendicular, this theta has to be 90 pi over 2. So cosine pi over 2 is 0. Okay, and since these square root terms are always positive, we can just throw them on that side to get p plus 2q plus 3r equals 0. Okay, keep that, that's equation 1, keep that. Okay, so that was looking at this first line. Now let's look at this second line. We'll do a similar approach. So again, cosine of this theta 1, call this theta 2, say negative 3p plus 2q, this 2 and this q, and this phi and this r, phi r, divided by square root of p squared plus q squared plus r squared times square root of 3 squared plus 2 squared plus 5 squared, I believe, is equal to 0. So again, now square roots being positive can be thrown on that side. So we just get negative 3p plus 2q plus 5r is equal to 0, and that is nothing but equation 2. So now what we can do is subtract equation 2 from, or rather equation 1 from 2. So we have minus p minus 2q minus 3r being equal to 0. So these two q's cancel out. Negative 4p plus 2r is equal to 0. So it means r is equal to 2p. So let's write q also in terms of p. You can substitute this into, say, equation any, you can substitute this in any equation. You'll get q is equal to negative 7 over 2 p. So now we can write all these p, q and r in terms of multiples of p. So now our general equation becomes x minus a over p is equal to y minus b over q, but q we found out to be negative 7 over 2 p is equal to z minus c over r, which is 2p. Now we can cancel p, we can divide everything on all sides by p, rather multiply all sides with p, And since p is non-zero, otherwise you'll have some finite term over 0 because p is in the denominator here. P can never be 0, otherwise it will defeat the purpose. So we can multiply by p and cancel p's in all the terms. So we have x minus a over 1 is equal to y minus b over negative 7 by 2 is equal to z minus c over 2. Okay, and now what we're going to do is, to ensure that this point always lies on this line, what we're going to do is let a equal negative 1, b equal the y coordinate of this which is 3, and z equal negative 2. So if you make that substitution, you'll have x plus 1 over 1 being equal to, this negative can flip the order, so 3 minus y over 7 by 2 is 3.5 is equal to z plus 2 over 2. And in case you're wondering whether this point is satisfying this equation for the line, we can plug that point in. Negative 1, if you plug that in, you'll have 0. If you plug in 3, you'll have 0. If you plug in negative 2 here, you'll have 0. So at the point negative 1, 3, negative 2, if you plug that in, everything will become 0. So this 0 will equal 0 will equal 0, and indeed 0 is equal to 0. So this point is satisfying this equation, and this is actually our required equation. Again, you can parameterize it and write it in form of a vector and 3D parameterization, but it's up to you now. And this is actually somewhat analogous to the fact that if you had a 2-point slope form, say x1 comma y1 and x2 comma x2 comma y2 in say 2D coordinate geometry, what you used to do, you used to have y minus any one of the points, say y1 is equal to the slope times x minus the same x coordinate of that point, x1. So you used to subtract y from the point which you wish to be on your line. So we're exactly doing the same. We're just having subtracting by exactly that. If you let ABC be the point you wish to be on the line, ABC instead of x1 comma y1. That's why the point we wish to be on the line, we take that for those coordinates instead of ABC, and it without any surprise satisfies the equation. Okay, so moving on to our final question number 18. They're telling us to draw a rough sketch of the curves y squared is equal to x and y squared is equal to 4 minus 3x and find the area enclosed between them. So this function actually looks familiar. It's actually reminiscent of x is equal to y squared. Sorry, y is equal to x squared. And y is equal to x squared is actually this simple parabola, like faced like this. You call this the x-axis and this the y-axis. But if you have y squared is equal to x, that is going to look just rotated 90 degrees. So it's going to look like this roughly, where this is the x-axis, this is the y-axis. And this parabola y squared is equal to 4 minus 3x. Since this x has a negative coefficient, a negative associated with the coefficient, it's going to be an inverted parabola. So it's going to be somewhat like this. But since there is this factor of 3, it's slightly more spread out outwards compared to y squared is equal to x. But in the exam you don't need to specify The diagram is never to scale when you draw. So I mean this diagram is sufficient. So they're telling us to integrate and find the area enclosed between these. So this point and this point, area enclosed is this junk stuff I've shaded. So, and for setting the integral, we need to know these meeting points where both of these curves are meeting. So we need to solve them simultaneously. So we have y squared is equal to x and y squared is equal to 4 minus 3x. You can basically subtract one from the other. You'll have 0 is equal to negative 2x minus 4, if I'm not wrong. Well, it's actually 4x uh, plus 4x minus 4. So x is 1, but when you plug that in, you'll have y squared is equal to 1. So if you take square root on both sides, you have to account for both the positive and the negative. So y is both the positive and the negative one, so plus or minus 1. So the 2 points of meeting of intersection are 1 comma 1 and 1 comma negative 1, because y is plus and minus 1. So I mean, if you look at the diagram, it makes sense, right? Because this point is 1 comma 1, this point is 1 comma negative 1, because it's below the negative y-axis region. And we need to set up an integral, and the way we're going to do that is we're going to integrate dy. So we're going to make slices like this, small infinitesimal slices, which we'll call dy. Okay, so we need everything in terms of, we'll need everything in terms of y, all x's in terms of y. So what we're going to do is actually solve for x in terms of y. So don't need to look at this first, it's already good. So look at the second. So y squared is equal to 4 minus 3x. So we'll have 4 minus y squared over 3, that is equal to x. So the way we're integrating, we're going this way, right, while integrating. Rather this way, because negative y is here, so we go this way rather. And we need to subtract stuff. So this outer curve minus inner curve will give the area enclosed. So outer curve is y squared is equal to 4 minus 3x, which we solved. We made x the subject. We got 4 minus y squared over 3. That curve subtracted from this lower curve, which is y squared equals x minus y squared, integrated dy from, what's the y coordinate, negative 1, right, to positive 1, because integration dy, so upper and lower bounds should be a functions of, should be y values. So now calculating this integral is actually very, very easy. All you have to do is just simplify nicely. So we have integral from negative 1 to 1 of 4 over 3 minus 4 y squared over 3 dy, which is nothing but 4 over 3y evaluated from negative 1 to 1 minus 4y cubed over 3, and this 3 will make a 9, evaluated from negative 1 to 1, which if you diligently simplify, you'll have 4 over 3 plus 4 over 3 minus 4 over 9 plus 4 over 9, which is equal to 8 over 3 minus 8 over 9, which is 16 over 9. And that's actually the area of the region enclosed. You can say square units for area, but that's actually the answer. So hey guys, I know it's been a really long video. Thanks for sticking up, and please like, share, and subscribe to my channel. Recommend me to your friends. I need to reach 100 subscribers. I'm working hard. Please follow me on Instagram, gamma_digamma. In the meantime, keep doing math, stay home, stay safe, peace out, and please stay tuned for my next video, which will cover the section C part of this ISC math paper.